Okay. Starting the stream later than I had planned to. But I am doing it because this is day 3 of live interview prep on Twitch. So welcome. I'll be solving some LeetCode questions today. Worthy of note is that I upgraded the stream a little bit. I've been tinkering around with some of the different plugins and stuff that you can do with OBS. So as I'm kind of adding things slowly. I don't want to overdo it, you know. So there's a daily follower goal now, which I'm excited about. I have no expectations of hitting it, but it's there just in case I do hit it. Then there's the latest follower that you can see, and then you can also see the song title and artist of the currently playing song. So I'm pretty hyped about those improvements. Hopefully that'll make the stream even just slightly more engaging. Okay, so jumping right into LeetCode, I just wanted to point out that on Saturday there are 2 LeetCode contests. There's the bi-weekly contest, number 83, and the weekly contest version or installment number 303. So I registered for both of those. I'm going to try to stream both of them live and just see how I do. You know, generally during these contests, depending on the difficulty of the problem, I might solve like the first 2. Sometimes I solve the first 3. If you're not familiar with the format of the contest, they give you 4 problems and 1 hour to solve all of them. And the problems are increasing in difficulty from the first one to the last one. So generally, I mean, I don't want to jinx it because I could end up doing really bad for no apparent reason. But generally, I'll get like the first 2 or 3. And, you know, depending on what the hardest problem is, depending on like what you need to know to be able to solve it, sometimes I can get that one. But that's more of a rare occurrence, and I'm always really hyped when it does happen. So I'll be live streaming LeetCode's bi-weekly contest 83, hopefully, on Saturday. And then also weekly contest 303 also on Saturday. So if you're interested in that, watch out for those streams because I'll be going live to stream that. Okay. So as per usual, I've selected a couple of LeetCode problems that look interesting to me. These 4 here that I have open, I might not end up doing these 4. Sometimes I get distracted by clicking through to the next suggested challenge after I finish a challenge. And then also before the end of the stream, I'm going to do where is it at? Explore? Where's the... Oh, here it is. So I'm in the middle... Well, I'm not in the middle. I'm in the process of going through the study plan for Dynamic Programming 1. So we did day 1 and day 2 yesterday and the previous day. And so today I'm going to try my hand at some point on these 3 dynamic programming problems. That'll probably be further on because I want to warm up my brain a little bit before jumping into dynamic programming. So that'll be coming up because I do kind of want to keep up my my streak of doing these daily dynamic programming challenges. Dynamic programming being one of the techniques that I struggle with, so I like that LeetCode has a study plan for it, and so I'm trying to go through that. One other thing that I wanted to do, let me see if I can do this real quick. I saw a really funny meme this morning on Instagram. There's some really, like, if you're into like coding and technical interviews and just the industry in general, there's the Coder Humor Instagram page, and they often post some pretty funny stuff. So let me grab this one and put it on screen just because I thought it was funny. So all right, let's see how good I am at OBS right now. Add an image, just call it temp. And Okay, here we go. So since we're preparing for technical interviews, this meme does seem appropriate. How hard would it be to get that to match the height of my camera? That's more of an OCD thing than any. Alright, whatever. Oh, wait, is it flipped? Why is it flipped? Huh? Okay. Let me try to unflip it. Oh, I know why it's flipped. It's flipped because I did, yeah, okay, I gotcha. I did that to it. So let's just have that over here. Not sure if that's going to be there the whole stream, but I think it's funny. So the technical interview, obviously, a very intense confrontation with technical coding, and then once you get the actual job, it's just like Christopher Robin playing with Winnie the Pooh. Not all of the time, but it's, yeah. I think you guys get the idea. Okay, so we've got our meme. No idea if there's probably not going to be a daily meme, but if I ever see something that I find amusing, I'll probably have it there. Okay, so let's jump right in. So I like to start off with something a little easier. So let's try this. Given a string S, find the first non-repeating character in it and return its index. If it does not exist, return -1. And yeah, so the length could be 100,000, and it only has lowercase letters. So this is probably just a hash map. Let's see, Python 3. So we'll just have scene equals set for C in S, scene dot, is it dot add? Yeah, I'm trying to do a little bit more Python so I can refresh my memory on just some of the libraries. Python set, I'm sure that that's it. Add set items. Yeah, there's a set add, and I'm assuming there's a, I can probably just use bracket notation to check if something's in there, right? Okay. So we're just gonna go through and we're gonna add every single character to the set. There's probably a one-liner for that. Like, let's see here. So s.split, is that right? Let's see if that works. Let's get all the test cases real quick. Okay, no, that's not right. It needs to be the letters. Do I just split on empty string? All right, Python string to list of characters. Like, there's no way that's not really simple. One-liner. Oh, okay, so I can just cast it as a list. If there's anyone here who's a Python expert and is like been face palming for the last minute or two, apologize. So this should work. Yeah, okay. So, oh, you know what? There's actually a better way to do this. There's a better way. So Python has something called counter. Where do I import that from? So counter is especially in like competitive like coding contests, counter can save you so much time just if you need to like quickly count the number of each element of something. So if you want to count the number of like each letter in a string, here we go. From collections import counter. So if we get a counter, then what we can do is we can just do counter equals counter s. And now the goal of the problem is to find the first non-repeating character and return its index. So let's just iterate I in range length of s. And the character at this position is going to be s sub I. And so what we want to see is how many of this character exist in the string. If it's just one, then the solution is I. So if counter of C is equal to 1, then we just return I, because we're supposed to return the index. Otherwise, return -1. All right, nice. So we knocked that one out pretty quick. Let's get a couple of run times. This is, surprisingly, this is fast compared to other Python 3 submissions. Like, it's consistently like 70, 80, 90% faster than the average Python 3 submissions. It's probably because of the counter. Counter is really nice. If I didn't explain it properly, counter gives you basically a table from all the elements of whatever you give to it and how many of them there are. So it's just a one-liner for what would usually take maybe like 2 or 3 lines of code. Excuse me. Every once in a while, my body and my brain just decide to try to breathe water instead of drinking it. So that's what just happened. Okay, so I'm probably gonna move on to the next problem, but let's see. So right, left, what's RLE iterator? I just want to just have a peek at these. Run length encoding. That doesn't strike me as super interesting to do right now. Minimum lines to cover points. This is like a geometry question. You're given an array of points, x and y, to represent points on an xy plane. Straight lines are going to be added to the xy plane, such that every point is covered by at least one straight line. Return the minimum number of straight lines needed. Okay. How many points do you get? How many points do you get? You get at most 10 points. So n squared, it's probably okay for this. N squared, so if you only get 10 points, even n cubed is fine for this. So, you know, if you had like a triple for loop over all the points to figure this out, that would get accepted. So my initial intuition for this problem is iterate over all the pairs of points. So actually my initial intuition is going to end up being n cubed. Iterate over all the pairs of points, and then if you figure out, like, you know, calculate the line that connects those two points of each pair, and then once you have that line, you can iterate over all of the other points and see if any of them intersect with it, right? And then you would know how many points that line connects, and you can use that as you're trying to compute the minimum number of straight lines needed to cover all the points. So basically, is this a greedy solution? Oh no. Related topics: array, hash table, math, dynamic programming, backtracking, bit manipulation, geometry, and bit mask. That's a lot of related topics. That's an interesting problem. Let me put that one on the back burner. I'm not gonna do that one immediately. Okay, let's take a look at this problem. So this is problem 695, max area of an island. You are given an m by n binary matrix grid. An island is a group of ones representing land connected four directionally. You may assume all four edges of the grid are surrounded by water. The area of an island is the number of cells with a value 1. Return the maximum area of an island in the grid. If there is no island, return 0. Okay, so this is a really good next problem to try. I think that generally there's two approaches you could take to solve this. Wait, let me just make sure I haven't solved this. Yeah, okay, I did not solve this. Approach 1, which is probably the one I'm going to do, is a breadth first search. So essentially, you're just going to go looking for the islands, and every time you find a new island, you keep track of how big it is, which is just the number of ones that it contains. And then as you jump from island to island, you're keeping track of what the largest island is that you've seen so far. And that's pretty reasonable to do with a breadth first search or a depth first search. The other approach to this is union find. So basically, union find is a data structure that lets you join nodes of a graph together such that they form a set which is disjoint from the rest of the graph. That is a little bit more tricky to code than a breadth first search. But I also haven't coded union find in a while, so it would be a good exercise. Let me implement this with a normal breadth first search first. Actually, you know what could be fun? I don't know how long I'm streaming for today. I'm gonna go for longer. I mean, as I mentioned, I have at least, at any moment, I have at least 3 more problems to do because I'm doing the dynamic programming for the day. So it could be fun to implement this all 3 ways. I think I'm gonna start off by implementing this as a breadth first search. So the way you would do that is, I always like to do this. I always like to just go ahead and grab the dimensions of the grid in variables so that I can reference it throughout the program. So once I get to the union find algorithm, I probably will have to do a little bit of review. Like, I understand generally how it works, but as far as the specific implementation, I might have to review a little bit at that point. Okay, so they guarantee that there is at least 1 cell in the grid because m and n are both at least 1. So because of that, we're safe to just go ahead and grab the 0th element of the grid. Okay, so now the next step is to just iterate over the entire grid, 1 cell at a time. And so I'm going to implement this as a BFS first, then I'll implement it differently as a DFS, and a lot of the code will look the same, only a small little pieces of it will change. So and I'll kind of explain that as I go along. So j is less than m plus plus j. Okay, if I got that right. So I'm gonna have a function. I'm just gonna like write my my different solutions. I'll implement them as their own function. So And so the solution to the problem is a integer. So let's do this. I think this will work. So we'll have an int like this, int best or largest, right? Because we're trying to find the largest island, the maximum area of an island, which is just the largest island. And we'll start it off at -1, and then we'll return largest at the end. And so one thing to mention here that I'm going to do throughout my program is, because if I discover a whole island, and I get the area of it, and then I keep that, and then I update my final answer. So int final answer is going to be 0. That's because if there's no island, the code says to just, the description says to just return 0. I don't know why I call it final answer, we'll just call it answer. So answer is 0, and then we'll return the answer down here. So what I was just about to explain was that when I uncover a full island, I want to delete it from the grid so that I don't encounter it again. So let's say that I iterate through all these spaces and I encounter this island right here, this like L-shaped one at the top. After I calculate, after I visit the whole island and determine that the size of it is 4, I'm gonna change all of these to zeros, and I'll take that 4 and I'll incorporate it into the answer. So what that's going to enable me to do is, in this double for loop, I only actually want to visit the node, the cell of the grid, if the value of that is 0 or is 1. So if grid ij is 1, then we know that because any previous islands we saw, we made them all zeros. Then when we visit grid ij, if it's a 1, we know that we're looking at a new island that we haven't looked at yet. And we need to visit the whole thing and get the area of it. So if grid sub I of j is 1, then we want to update our answer. Answer is going to be the max of the current answer and BFSing from this tile. So we BFS, we give it the grid, we give it I, and we give it j. And what I'm gonna try to do later is I'm gonna implement this as a DFS, and what I'll do is I'll just comment this out and I'll do this. Right. So the BFS function will return the area of the island, and it will also be responsible for setting all of the cells of that island to be 0. And the DFS function will do the same thing. It'll return the area of the island, and it'll set all of the cells that are visited to 0. So what's going on here? Technical difficulties. Okay, there we go. So we don't have a DFS yet. We're working on our BFS solution now. So for the BFS, as input we get the grid. So we can just copy this parameter up, and we get an I and we get a j. So the first thing that we want to do is set up our queue. So for BFS, we're going to have a queue, and the queue is going to contain a vector of int. Yeah, I think the queue can just contain pairs of ints, I think. It just needs to have the coordinates of the tiles that we're visiting. And then we're going to have while the queue is not empty. While the queue is not empty, we'll continue to process the cells of the island. So we need to prime the queue. Okay, actually, so So this is actually not what we need. We can actually just do like size here. Start it off at 0 and then return size. And what we'll do is in the queue, whenever we're processing a cell of the island that we haven't looked at yet, we'll increase the size by 1. So we need to prime the queue. The way we prime the queue is we just start with the I and the j that get passed to this function, which is it's basically the non-zero grid cell that was found by this double for loop that's just going through the whole grid. So auto next equals q.front, q.pop, int. Here, let's call these two I start and j start, and then we'll push onto the queue those, and that just means that we can call them I and j here. Okay, so we have that. Another thing that we want to do is we want to so I think the way that I want to approach this is an invariant, is I only want to put things in the queue that are unvisited cells of the island. And so if I make that an invariant, then I can do ++ size here. But that just means that down here, below like this part of the while loop, I need to make sure that the only thing that I push into the queue is like unvisited cells of the island, and we want to make sure that we push them in only once. So I think that's going to work just fine. What I'll do now is down here, as part of the priming, we need to mark this tile as being a 0. So that just makes sure that we don't visit it again. We got our ++ size, and then now let me get my directions. So I wrote this up a couple of days ago. I don't think I'm going to explain it all again. Maybe I will just very briefly. So because we're going 4 directionally, I'm creating pairs of numbers that represent each direction that we need to go. So you have your 1, 0, which makes you go down. You have your 0, -1, which makes you go left. You have -1, 0, which makes you go up. And you have 0, 1. So we're just going to look at the consecutive pairs of this right now. So for int idir equals 0, idir is less than 4, ++ idir. We're going to get our next I and our next j. Next I is going to be I plus the dir of idir. And then our next j is going to be the current j plus the direction of idir plus 1. Like that. That'll get them all. So we have to make sure it's in bounds. So if next I is less than 0, or next I is greater than or equal to n, or next j is less than 0, or next j is greater than or equal to m, we continue. But importantly, we also continue if the cell at next I, next j is a 0 already. So, or grid of next I, next j is equal to 0. So if we get past this if statement, we know that we're looking at a cell that's in the grid, and we know that we're looking at a cell that is a 1. So with those being the case, we add it to the queue. We know that this is a valid node of the island that we need to visit, and we're going to make sure that we only visit it once. The way we do that is as soon as we push it into the queue, we're going to mark it as visited. And I think, depending on how you like to write your BFSs, there's different ways you could do this. There's like different orders that you could write these. but I'm pretty sure that this will work. So, is that everything? Is that everything that I need to do? So, the BFS, it keeps track of the size, increases the size every time we visit a cell, returns the size. It makes sure that we're only visiting every single part of the island exactly once. And that's where we plus the size here. And then we're starting our answer off at 0, and we're increasing our answer every time we find a new island size that's larger than we already have. And then we return it. So let's run this code. I'm sure it's not completely right. Okay, so probably have some syntax errors. We need another greater than sign here. Not entirely sure what the name of that operator is. I start right here. Oh, okay, we don't have N and M. I'll just pass them in. I, J, N, M. Okay, so we pass the first example. It looks like the test cases are fairly limited. Well, actually, this test case is a nice one. Like, it's got a bunch of different islands in there. So this test case is just 0. So let's use the example test cases, but then let's just add one final test case, which is, let's add 2 more test cases. Let's add the case where the grid is just 1 by 1 with no islands, and let's add a case where the grid is 1 by 1 and it just has a single island of size 1. So let's run those. And 6001, 6001. Okay, so I think that's it. That works for the BFS solution. So I'm going to submit that. I feel pretty good about that. Yeah. So we're good. We are good. Now what I want to do, just as like an exercise for myself, but also potentially useful for other people watching, is we can, instead of BFSing to find the islands, let's DFS to find the islands. So let's write a DFS function. And let's try to make the interface of the function basically the same. I think we should be able to do that. So here, let me copy this, just repaste it there and change this to DFS. So let's try to get the answer in a DFS. So some of this code is going to be the same. We still need to, even for the DFS, we still need to look above, below, to the left, and to the right of the current tile. So we still need this. So similarly to the other solution as well, let's just go ahead and as soon as we get into this DFS call, we'll just mark the cell that we're currently at, the cell that we're visiting, we'll mark it as 0. Okay, so these lines of code are going to be exactly the same. We need to go in all 4 directions, and we'll get the next I and the next j, and this is going to be the exact same as well. We want the next I and the next j to be in bounds, and we want to make sure that it's a 0. So assuming that we get past that if statement, now what we want to do is we want to DFS the grid starting at grid ni, grid nj. Oh, wait. It's just grid ni, nj, n, m. There's a couple more things that we need to do here. So DFS is going to return the size of the island. And we want it to return the size of the island because that way it has the exact same behavior as the previous BFS function that we wrote. So if we want it to return the size of the island, we need to keep track of the sizes of the islands that are adjacent to this cell, basically. So int size, and if you look up here, we also have an int size. We start off the int size as 0, and then every time we visit a cell of the island, we increase it. So we're going to do the exact same here, but the important difference is as soon as we enter this DFS call for a specific cell, that is us visiting the island. So we actually start off the size at 1. And then we return the size down here. So we start the size off at 1 to count for the current cell that we're visiting. And then every time we DFS, either up, down, left, or right, we take our current size and we increase it by the number of cells of type 1 that branch of the DFS is able to find. So DFS is going to go potentially in 4 directions. It probably actually won't do that simply because we're always starting in the top left cell of an island-ish. Or at least we're starting in one of the top cells of the island. That's basically guaranteed. But we'll still do it this way. So this might be it. So we zero out the grid at ij. We start our size off as 1. Then we go through all four directions. If the tile is visitable, then we visit it right here, and it's going to return the size of all the cells containing 1 that it finds, and we just add that to the size. And because of how we're handling just immediately zeroing out the grid and making sure that we don't visit anything that's 0, this should, unless I have something wrong here, this should ensure that every single cell of the island is visited once, in which case our final size should be correct. So let's run it. Let's see if that's the case. Oh, interesting. So that's also a notable difference between the BFS function and the DFS function, is that the BFS function takes your iStart and your JStart, and then it has a while loop where it does the level order traversal, visiting all the nodes. But in the DFS, we could call it iStart and JStart, but really DFS, like every single call to this function is a visit to a cell in the island. So we can just do ij. One way to think about it is that the contents of this DFS function, like the entire contents, represents one iteration of the while loop in the BFS. Okay, so we have that. Let's run it. Okay, so we do pass the test cases for the DFS. Let's submit. Okay, so that worked. That worked. It's basically the same runtime. It looks like it did use a little bit less memory, which is nice. Okay. All right, so last but not least, I want to solve this problem using union find. And I have not written a union find data structure in some time, so let's review together. Hold on, let me just respond to a quick text. All right, so union find data structure, because there's like some optimizations you can do. There's path compression. Let's see. What do we want? Where do we want to venture to? We could go to Wikipedia, Geeks for Geeks, Techie Delight, Hacker Earth. There's a lot of resources. Is it probably safe to assume that Geeks for Geeks probably has some of the best information? Let's just go take a look. So a disjoint set data structure keeps track of a set of elements partitioned into a number of disjoint non-overlapping subsets, right? Right, so the union find algorithm lets you take a disjoint set data structure and either find which subset a certain element is in, or it will let you union two subsets together. So I used to have this code memorized. I might still be able to at least get started without looking at sample code. Okay, so we're gonna have two functions. We're gonna have union and we're gonna have find. Union is gonna return a bool. So it's gonna take the let me just code this out and then I'll try to explain what's happening. Vector of int parent. And then I'm going to call these U and V because in general, like when you're dealing with union find, you're kind of thinking of it in terms of graph theory and you're not really thinking of it in terms of a two-dimensional grid. So I like to use I and J when I'm dealing with a two-dimensional grid. Some people like to use R and C. Some people like to use X and Y. I'm an I and a J kind of person. If I and J are already in use, then I would probably do RC. I don't know, I'd probably just do whatever I'm feeling. But since a union find data structure is, it's a graph theory concept, in graph theory, you usually use U and V to refer to two different nodes of a graph. And so what we're going to be doing is, even though this is a two-dimensional grid, we do have a graph here where the nodes are the cells and the edges are basically every single cell has an edge going up, down, left, and right. So you do have a graph here. And so what we're going to end up doing is if we discover two ones that are next to each other, we're going to union the set that the first one is in with the set that the second one is in. So man, I really wish I had, I do have paint. Let me see, I got paint. So, let me see if I can kind of explain this a little bit. So let's say this is a node in the disjoint set, this is a node in the disjoint set, this is a node in the disjoint set, this is a node in the disjoint set. In the case of our problem, max area of island, these nodes are cells in the two-dimensional grid. So right now, each of these four nodes is in its own set. None of these nodes are connected in like the union find sense, right? But then if we try to take this top left node and this top right node, and if we were to union them with the union find algorithm, that puts them together in a set that contains both. Similarly, if we were to take this bottom left node and this bottom right node and union them, that would put them together in a set containing both. But now this is where union find is extremely useful. Now, after we had this, let's say we wanted to union this top left node with this bottom left node, it doesn't actually do this. What actually happens is because these top two are already unioned and these bottom two are already unioned, you end up with a single set containing all four. So that's a really rough explanation of what the union find algorithm does. So now we just have to implement that. So the way that it's usually done is you usually have a parent array or vector, and it's the parent array or vector is the same size as the number of nodes in the graph. And it would look kind of like this, vector of int parent, right? Then the way that you can use a vector of ints to keep track of this data structure that I just described over in Paint, the way that you can use a vector to do that is the values. So at a high level, the way it works is every single set has a node that is the representative, effectively, is how it's going to end up working. So let's say that you have, let me just create this graph again. I'll create these two. And let's see, Paint is going to let me draw an arrow, I assume. Yeah, it is. So when you union this top left one and this top right one of these two nodes is going to become the parent of the other. So you're going to end up with an edge between them in the disjoint set data structure. And so similarly, the direction doesn't specifically matter. Similarly for the bottom two, when you union them, one of them is going to become the parent of the other. Now, when I union the top set with the bottom set, what's going to happen is we're going to get another edge that points them up. There's a bunch of different edges that could do this, but we'll just use this one. We'll draw that edge. And now all four of these are part of the same disjoint set, but if you follow the direction of the edges, you can see that this one in the top right, this is actually the representative node of the whole set. And so anytime you were to go to, let's say that you were to go to this bottom left node, the bottom right node, or the bottom left node, or the top right node, if you were to go to any of those three and ask them what their parent is, or what their like top level parent is for the whole set that they're in, they would tell you this one in the top right. They'd be like, our representative is this one in the top right. What a lot of union find data structures actually end up doing, let me delete those arrows, is let's say that you have a, hold on, how do I make my brush bigger? I'm not a Paint Pro, unfortunately. Let's say that you had like this arrow here and then this arrow here. And so basically what that means is that these three are in a disjoint set together, where the representative of the set is this top right node here, but there's actually another representation of this disjoint set that means exactly the same thing, and that would be if this node was also pointing up here. So one way that a lot of union find algorithms are built are that anytime you basically do anything, it tries to compress paths, and that's called path compression. So theoretically, you could have a situation like this, where this node has a parent of this node, this bottom left node has a parent of this top left node, and then the top left node has a parent of the top right node. And so you have your ultimate parent of this guy. This guy's the ultimate parent. But as you're performing operations on the disjoint set, what you really want to do to make things faster is you want to compress those paths so that all of them are pointing to the ultimate parent. So the ultimate parent, like the representative of the disjoint set, doesn't change. Oh shit. I didn't have my paint screen visible that whole time, bro. What a bad streamer. Yeah. So Okay, so once again, this node is going to be the representative of the whole disjoint set of all four of these. And so you're going to have these edges on the graph. You could have an edge here, you could have an edge here, and you could have an edge here. And so all four of these, so this is the union find, this is the disjoint set with union find as the algorithm. All four of these are in the same set, and the representative of the set is like the ultimate like parent, which is this one in the top right with a green circle around it. This representation also means the same thing. If you have these edges, it's exactly the same. All four of them are still in the same set, and the ultimate parent is still the representative in the top right. But you can actually compress these paths even more. So right now, if you were to go to this bottom left node and you were to ask it, hey, what's the representative of the set that you're in? He would have to first go up to the top left node and then hop over again to the top right node. So he would have to take 2 steps to be able to answer that question, like who is your parent, who's your representative. So we want to actually compress the paths even more. And ideally, we can just eventually have all of the elements of the set pointing to the representative. And all of that is to say that this parent vector that we're going to use is exactly those relationships in the disjoint sets. Every single node has an edge that points to its parent, but ideally we want every single node that's part of the same set to have an edge to the same node, which is the ultimate, like the top level ancestor, the representative of the set. So that's what we're trying to accomplish. So the 2 functions that you need are, you need union and you need find, and that's why the algorithm is called union find, obviously. Int u and int b. Okay, so we want to implement find first because find actually gets used by union. And so what find does is find only takes one node. Find takes the parent array, which represents the graph of the disjoint set data structure. And it takes a single node, u, and the job of find is to return the representative node of the whole set. So in order to do that, find might have to jump through several parents to find who the ultimate god, the ultimate like ancestor node is. And a nice optimization that you can do in the find algorithm is you can, after you discover like what the ultimate parent is, then you take the first node that you looked at and you update its pointer to be pointing to the top node. That's the path compression part. Then the other thing that's important is this parent vector, parent sub I, is going to be, if it's greater than or equal to 0, let's see, there's like a nifty way to write this, because you want to store some information in the parent array. You want to store like what the parents are, but you can also use this to store an approximation of the size of the tree. And I bet Geeks for Geeks talks about this. So if we scroll down, union by rank, that's what it is. So path compression is what I talked about. In the disjoint set data structure, there's multiple different, there's like basically an exponential number of ways you can represent the exact same disjoint set. but the most efficient is if all of the nodes of a set have their parent pointer pointing to the representative. And so you accomplish that by using path compression. Union by rank is it's part of the union function that we are going to have to write. Effectively, union by rank has to take two different subtrees of the disjoint set, two different sets, and it has to put them together. And union by rank tries to optimize the efficiency of the data structure by either making one of those, it chooses which of those two becomes the parent effectively. Okay, so I'm going to try to implement these from memory. Let's see if I'm able to do so. So if parent sub I is less than 0, we want that to be the rank. Oh, I remember how to do it. Yeah. So if parent sub I is greater than or equal to 0, then that's a legitimate pointer to a parent, right? It's a 0 indexed pointer. So 0 then here, let's do it this way. Let's just write a little bit of comments. If parent sub I is greater than or equal to 0, then parent sub I is a pointer to the 0 indexed parent of node I. Else, if parent, the only other possibility is if parent is less than 0, then what that means, this is very important. If parent sub I is less than 0, that means that node I is a representative of a set. And the absolute value of parent I equals the rank of the set. And the rank of the set is kind of a confusing concept. I'm not even sure if I fully understand it, but if you implement it properly, it helps you sort of optimize the merging of two separate sets together. And the nice thing about honestly, the main advantage of the union find algorithm is that you get to merge two sets together in, I don't think it's technically constant time, but it's like close to constant time. It's extremely quick. Let's see. Hold on, let's just look that up real quick. Union find algorithm complexity. I bet this is going to have Wikipedia as the first source. Stack Overflow as the first source. Okay. What is the time complexity of performing n union find operations? Oh, why is it n log n? No, it's this. It's log star of n. Yeah. So, why is this not the accepted answer? Hold on a minute. Sign up with Google. I already have a Stack Overflow account. Okay, I just wanted to vote up this one. So the idea is that if you use a really naive union find algorithm, your time complexity for performing a union is going to be n log n. And that's related to the reason you have a log in there is because your tree has like a height. But because you use union by rank as the first optimization and you use path compression as the second optimization, you actually improve your time complexity significantly to n times log star of n. Yeah, I don't know a lot about log star of n, but the most important thing is that it's a very slow growing function, much slower than log of n. So union find is basically the most efficient way to do stuff like this. So in other questions, in this question, you can solve it using BFS, which we already did. You can solve it using DFS, which we already did. And the other way you can solve it, or at least one of the other ways that I know of, is using the union find data structure. That's option 3. But then there's some problems that you can't solve with DFS and BFS, and you have to use union find. Hey, what's up? Not enough study streams. I'm trying to get more into streaming. I thought that starting off by doing these daily interview prep streams would be a good way to get into it. But once I do get a job, which hopefully will be sooner rather than later, I'm not going to stop streaming. I'll find some other stuff. I'll still stream coding, but it just probably won't be LeetCode. I have some, I'll probably be doing like web dev or something like that instead, and maybe still come back to the LeetCode every once in a while to like stay up to date and stuff like that. But no, like I do want to stream coding, and I'm just using my interview prep as an excuse to do it. So right now I'm trying to implement a union find algorithm to solve this problem. I already solved it using BFS. This is very similar code to like what I wrote yesterday and the day before for some problems. And then I also solved it using DFS, which is it's shorter even than the BFS solution. But then another possibility as a solution to this problem is to solve it using union find. So I'm trying just as like an exercise for myself. Like I already got it accepted. This first submission was my BFS submission. The second submission was my DFS submission. And so now I want to solve it using union find. No, it's not hard to learn. I was trying to explain it in Paint. These are my beautiful diagrams right here. I was trying to... So I would suggest, if you want to learn union find, there's probably some good YouTube videos out there. Also, I'm trying to upgrade my stream. So I'm trying to upgrade my stream so that I can actually draw by hand. I'm getting one of those like tablets that just has a pen and like a flat surface and you can draw. And then when I do diagrams like this, it should be a lot easier to do. But no, union find is not hard to learn. And it's actually like really cool in my opinion once you understand what's happening there. I could try to explain it again if you want me to. It's basically an efficient way to merge trees together when the only thing that matters is that so you basically end up with a bunch of little trees, and every single little tree represents a set of elements of the input. And then if you want to merge two of them together, like usually that would take like n squared time or whatever, and then the disjoint set algorithm lets you do that a lot more quickly. And the reason we want to use that for this is because so this two-dimensional grid here in the input, even though it's a two-dimensional grid, it can be represented by a graph where every single cell in the grid is a node in the graph, and the edges are just pointing up, down, left, and right, 4-directionally, so that you can visit the neighboring nodes of the graph. And so because we can represent a 2D grid as a graph, you can use union find to merge cells together, or union cells together. So let's say that we were looking at this L-shaped island here on the left, and we know that there's two ones next to each other on row 3, right at the top of the L. What we can use union find for is to say, take all of the ones that are connected to the one on the left, and take all of the ones that are connected to the one on the right, and combine all of those together so that we can figure out the entire island. That's kind of the high-level idea of why union find will work for this problem. Okay, so I was just defining what my data structure does. So if parent sub I is greater than 0, then parent sub I is a pointer to the 0 indexed parent of node I. And so let me go back to Paint for a second. What that's basically saying is if you look at these 3 nodes that have pointers to the node in the top right, those would have parent sub I being greater than or equal to 0, because each of these nodes is pointing to the parent node of the tree. However, the parent node of the tree would have a negative number in the array. So if I go back to the code, the parent node is going to have a negative number. It doesn't actually have to. So I was mentioning earlier that there's like a naive way to implement union find that does work, but it ends up being slower. Then there's 2 really important optimizations that if you optimize your union find using them, it becomes like significantly faster. The first one is path compression, and the second one is union by rank. And so we're going to be implementing both of those. So union by rank means that every single tree in the set in our data structure needs to have a rank associated with it. And so the way that we keep track of what the rank is any member of this parent array that has a value of less than 0 means that that node is the representative of the set for that set, and then the absolute value of whatever parent sub I is going to be the rank of the set. So you could have, like, let's just say that hypothetically speaking, the parent array equals 0, 0, 1, negative 3, 1, 0, 0. Yeah. Okay, let's just do it like this. So what does this mean? So since the first element is less than 0, that means that this node in the graph is the representative of a set, and the rank of that set is 3, since the number is negative. Everything else here in this diagram is greater than or equal to 0, and these are, since they're greater than or equal to 0, these are effectively pointers to their parents. So I could, here, let me go back over to Paint for a second. This is a very high, very, I don't even know what the word is that I'm looking for, technical stream using Paint. So the parent array equals negative 3, 0, 1, 0. So let me show what that means as a graph. So because our parent array has 4 elements in it, that means we have 4 nodes. 1, 2, 3, 4. And just so that we know, let's give these an index. So we have a 0, 1, 2, 3. So these numbers here, 0, 1, 2, 3, means that's that node's index in this parent array. And so now that we know that, we can actually illustrate this array. So let me get a different color. So negative 3 means that node 0 is a representative node of the set. So it has and the rank of it is 3. And it's a parent. So because it's a parent, we can, it's not a parent, it's a representative. So that's the representative. That's the only representative in this graph. But the idea of this disjoint set is you could have multiple of these, and then at some point you might end up needing to union them together. Index 1 has a parent. Index 1 is greater than or equal to 0, which, as we mentioned, means that it's a pointer. So what that means is that this node has this node as a parent. Let me use a different color. The index 2 in the array is a 1. That means that this node has this node as a parent. And then index 3 of the array is a 0, which means that 3 also has this node as a parent. I drew it like that just so that I'm not intersecting the edges of the graph. So this is what -3, 0, 1, 0 means in the parent array. Something that I do want to point out is that since we're going to be using path compression, what's actually going to happen is this edge that goes from node 2 to node 1 is actually going to be rewritten so that it points to node 0 instead, because that means the exact same thing. All that matters is that the only thing that matters is that all 4 of these nodes are in the same set, and that if you follow the pointers, you ultimately get to the representative of the set, which is node 0. So if you follow the path from node 2, you get to node 1, and then you get to node 0, which means that the set that 2 is in has a representative of node 0. But if you want to optimize the efficiency of this, you actually end up deleting that edge and updating node 2 to point to node 0 instead. That's the idea. And so that's what path compression is. It's basically every time you have to like jump multiple steps to get from any node to the representative of the set, which is the root of the tree, you try to rewrite those edges of the graph so that they just point directly to what the to who the representative is. So let's try to do that. So now that we talked about all that, we literally just okay. So just to explain, find returns the index of the representative node of the set containing node u. That's what find does. So if parent of u is less than 0, then it returns itself. That's the idea. So any node that has a negative value in that parent array is the representative node of its own set that it's in, and so we just return itself. Otherwise, parent of u is greater than or equal to 0, and so we want to follow the chain. So const u let's see. So what do we want to do here? We want to get the representative index, const representative. And so this is where it gets kind of cool. Watch this. So the way that we get the representative of the set that u is in is we just call find again recursively, and we give it u's parent. Right? So find is a recursive function. So since we know that u itself is not the representative, here, just to make this easier to understand, what I'm going to do is let's just rename this function to find representative. And then we'll call this union sets. So find representative, it's supposed to, it'll return the representative for the set that node u is in. If the parent of u is less than 0, then u is the representative, so we return it. Otherwise, the way that we get the representative is by recursively calling find on u's parent. So we just jump up one. And so, okay, I keep forgetting to update this thing here. So this is how the find representative function works. So basically, you could be like really low down in the tree, and when you call find representative, you have to basically traverse up to the root of a tree. And also, when I say tree and set, in the case of union find, those are basically the same thing. Those are interchangeable terms. So, okay. So now that we know what the representative is, we want to return it, right? But we can actually add path compression to the algorithm with one more line of code. And this is what I think is really cool about union find, especially this specific implementation of it. Now that we know what the representative is for u, because we recursively went through all of the parents and until we got to one, the base case where the value is less than 0. Now that we know what the representative is, we can compress the path really easily. And the way we do it is like this. Parent u equals representative. Done. There's the path compression right there. Some people who are coding this up in a speed coding situation, like a contest, they do this. You can actually do the assignment and then return the representative in one line of code. Oh, actually, you know what? I think in a speed coding situation, you could actually do this. And you wouldn't call this find representative. You would call it just find parent of u. So you can write it that way if you're trying to implement this function as quickly as possible. But while that's valuable in some situations, right now I want the code to be readable. So we'll do it this way. So for find representative, if the parent of the node that we're looking at is already less than 0, then it is its own parent. It is the representative of the tree and the set, so we return it. Otherwise, we recursively call find on the parents of u, and we keep going up until we finally get to the representative. Eventually, the base case will happen, and we'll come back down, and each node that we passed along the way will know what the representative is for the entire tree, and so we just update it. We compress the path, and that means that next time, because we compress the path by overriding the edge with the representative, next time we call find representative on the exact same node, we get there much faster. That's the idea. So that's how find representative works. So the next step is union sets. The next step is union sets. So unioning the two sets means that you want to take all of the elements of set of like the one set, and you want to take all of the elements of another set, and you want to combine them all so that they are all in the same set. And the way that you do that with the union find, which is why it's so efficient, is because you just have to take, because you have two sets, you're dealing with two trees. Each tree has its own parent, it has its own representative. You just have to take one of those trees and like put it underneath the other one, right? Let me draw this out in Paint. So let me draw it out. So you got two trees. You got tree A and you got tree B. And let's just, and because we're using path compression, we already know that this is, whoops, that's not what I meant to do. We'll do it like that. We'll use green, I guess, for the edges here. Let me just, can I delete all that? I can't. I'll delete this because it just looks like some kind of weird pig snout that has 4 nostrils. I'll leave this diagram because that's useful. Okay. So we switch back to green. We have 2 sets. We have set A on the left, and we have set B on the right. Both of these sets have a parent node. U is going to be the parent node of this set, and V is going to be the parent node of this set. Also, the reason I'm going through this in such detail is because I haven't done union find in a while, and so I'm explaining it to myself as much as I hope that I'm possibly helping anyone who's watching understand it as well. Plus, this will be going on YouTube, so I might have a YouTube video called like union find explanation or something like that. So we've got those 2 sets. This right here is set A. This right here is set B. And so now we want to union these. So the way we union the 2 sets is, it's actually really easy. If you think about it in terms of the parent array, the parent array at index U is less than 0, indicating that it's its own parent. The parent array at index V is also less than 0 because it's the representative of its set. And so you have 2 sets of size 3, and the representatives of those sets are nodes U and V. Now, if we want to merge these 2 sets together so that all of the nodes in both sets are now in one set, all we have to do is decide whether or not we want U to be the representative of the merged set, or whether we want V to be the representative of the merged set. And so if I switch back to the green, let's say that we decide that it's better for U to be the representative of the merged set. All we do is we draw an edge from U to V, and we're done. Now these sets are merged. So it's actually, merging sets is, you can kind of think of it as a constant time operation. And you'll see in a second why it's not quite constant time, because we do call the find function. And so the find function has to find parents and compress paths, and so that's why you end up with like the log star of n complexity, which is still really good. It's the fastest way to do stuff like this, the fastest known way at least. So you could also decide that it's better for V to be the representative of the merged set. So then you would take U and you would change it so that its parent is V, and so now all 6 of these nodes are all in one set, all in one tree, and V is the representative. And so after you do that, after you update U's parent to point to V, you're technically done with the union operation of union find. But future calls to the find function, remember how the find function does the path compression? Future calls to the find function will ultimately update these edges of these 2 nodes so that they will now point to V instead. And so what you end up with is a really flat tree. And that's what you want. You want a flat tree, so because that enables you to look up what the representative of a set is really quickly for any node in the entire graph. Okay. So I'm just going to leave this diagram looking kind of like this, and let's switch back to the code and implement that, because this is actually where the union by rank thing comes in, and I'm a little bit fuzzy on that. So let's see here. How long have I been up for? Okay, I've been up for 1 hour and 30 minutes. My water bottle is empty. You need to use the restroom. But let me delay those necessities for a short while longer. So we're looking now at the union function, which is half of union find, right? Union find is literally just a function that can find and a function that can union. Once you have those 2 things, you've got union find. You've got disjoint sets. So the union sets function the important thing to keep in mind about it is when you call union on any two nodes in the graph. So if we look here at the two-dimensional grid of islands, and we look at the this L-shaped island here on the left, let's say that you're unioning the top two ones together. The important thing to keep in mind is those top two ones might not be the representative of the set that they're in, and so the solution to that is, as soon as you get this call to union sets, the first thing you do is you just find the parent of each node like this. Not the parent, sorry, the representative. And there's no reason to keep the original U and V. When you're unioning the sets, literally all you care about is the representatives. Because once you know what the representatives are, as I was showing in Paint, as soon as you know what the representatives are, you just take U and you point it to V, or you take V and you point it to U. Right, over here. So you can make U and point it to V, in which case V is the new representative of the entire merged set. Alternatively, this top edge here could go in the other direction, and U could be the representative of the entire merged set. All right, so the first thing we do in union sets is we find the representatives. So I renamed these functions to find representative and union sets just for readability. In most implementations, especially if you're trying to code this up quick, what you would do is you would just call them union and find. If you really feel like you're in a time crunch, you could just call them U and F, you know, you call it whatever you want, but I'm trying to make it readable. So let me add a comment. So we added a comment for what find representative does. Union sets. Union sets, it doesn't need a really descriptive comment. It basically merges all the sets, all the nodes in the set containing U with all the nodes in the set containing V. It is important to keep in mind that a lot of times when you implement union sets, you actually want to know whether or not that was successful. And what I mean by successful is if U and V are already in the same set, then you don't actually need to do anything. But sometimes when you're calling union sets from your actual program, you need to know whether or not those two were already, whether or not the union was successful, basically. So the way you do that is if U equals V, return false. So if U equals V, that means that we know already that the representatives of both trees are the same representative, which means that it's the same tree, it's the same set, and we don't have to do anything. We just return false, saying that effectively saying that the union operation failed because it wasn't necessary, right? That's what that's doing. Then at the bottom of the function, after we do all the other stuff, we return true. We return true down here. So that's what that does. Okay. Now this is the part where I'm the fuzziest of all. This next part. We actually need to decide who should be the new representative. Should it be U or V? Because either of those would work, right? You could actually do it naively and not even bother about union by rank, and your code would still be okay. It just wouldn't be like as efficient as it could be. You know, if you're trying to like 100% this test, and you're trying to like be as efficient as you possibly can be, then you can use union by rank, and you can intelligently decide whether you want U or whether you want V to be the representative of the new set. Let's just assume for a second we didn't want to do that, right? what would we do? We would do parent of u equals v. Is that it? Is that all we have to do? That might be the naive solution, right? Well, naive's not even a good word for it. Like, it works fine. In fact, for a lot of union find, for a lot of LeetCode questions and contest questions where union find is used, you can probably get away with just doing this. But union by rank is a little bit better, so I want to do that. So let's think about it for a second. So one thing that I didn't mention yet is that this parent array starts off as all zeros. Let's create it somewhere. Let's comment this out. Let's create a parent array up here. So vector of int parent. Size n times m. So the other thing that's kind of finicky about this specific problem that you have to think about is that your grid is your graph is a two-dimensional grid, right? So you have n times n nodes. So the size of the parent array is n times n, but then once you have that, once you know that the size of the parent array is n times n, you also then need a way to convert from coordinates ij to indices in the parent array. It's actually kind of straightforward to do. Int get parent get index in parent array. You only need 3 pieces of information to do it. You need I, you need j, and you need n. And so the solution to this problem is literally just return I times n plus j, I think. Or is it j times n plus I? So yeah, you want to make sure that you're getting a unique yeah, no, it is right, because I corresponds to n. And so if I is 0, we're in the top row, right? If I is 1, we're in row 2. So we want to add that many of n into it. So this is it. And then so coordinate 0, 0 will just produce 0, 0. Coordinate 0, 1 will produce 1. And then eventually you'll get to like coordinate eventually you'll get to coordinate 1, 0, and you'll just get n. So this is right. This is how you can convert from the ij coordinates to an index into the parent array. So I just created a util function for that. Okay, so the size of the parent array is n times n times m, and the starting values are all -1. And the reason the starting values are all -1 is because at the very beginning of this process, every single node in the graph is in its own set by itself, in which it's the representative. So if you remember up here, I defined what the parent sub I means. If parent sub I is greater than or equal to 0, then parent sub I is a pointer to the 0 index parent of node I. Else, if parent sub I is less than 0, then node I is a representative of a set, and the absolute value of the parent sub I is the rank of the set. So by initializing the entire parent array to be -1, What we're doing is we're saying every single node in the graph is in a set by itself in which it's its own representative. And we're also saying the rank of all of these sets is 1. Now, what is the rank of a set? The rank is an approximation of how many nodes are in the set. And the reason we use the rank is because it helps us decide, if we go back to Paint, if we know how many nodes are in set A over here, and if we know how many nodes are in set B over here, that can help us create have an approximation as to whether or not it's better for U to update its parent to be V, or for V to update its parent to be U. Okay. All right. So, decide who should be the new representative. Is it U or V? So that's what we're going to do. If parent sub U is greater than parent sub V, that means that the tree represented by V has more nodes in it. Let me just double check here. Let me just Google union by rank. I just want to make sure I'm doing this right. Okay, yeah, so union by rank. Uses find to determine roots of the trees. We already did that. If the roots are distinct, the trees are combined by attaching the root of one to the root of the other. If this is done naively, such as by always making x a child of y, the height of the trees can grow as linear. We can optimize this by using union by rank. Hold on. At some point, I'll get used to doing that. So union by rank always attaches the shorter tree to the root of the taller tree. So let's think about that. Let's go back to Paint for a second and try to figure out why that might be best. So let's say that we had some more nodes here in tree B, right? We could have another node here too in tree A. So we've got an edge here. We've got an edge here. We've got an edge here. Now, B is the taller tree. B is also the larger tree. So union by rank. So union by rank always attaches the shorter tree to the root of the taller tree. Wait, is it shorter and taller, or is it size though? If we union two sets and both trees have the same rank, the resulting set's rank is one larger. I see. Oh, okay. Yeah. So you don't actually like. You don't actually add the two ranks together. You just take the rank of the tree that's gonna be the root, and you add one to it, right? That's what you? Yeah, okay. And they use the word rank instead of height or depth because path compression will change the heights trees over time. Okay, that makes sense. If both trees have the same rank, the resulting set's rank is one larger. Okay. So let's implement that. If the trees have different ranks, the resulting set's rank is the larger of the two. Okay. Okay, let's think about this. So in this case, so in the case over here in Paint, we would want to make U a child of V rather than make V a child of U. So the direction of this arrow at the top here that I drew earlier is correct, because that keeps the rank smaller. That's the idea. Okay, let's see if we can implement that. So if the parent of U is greater than the parent of V, this means that V's rank is higher. U has smaller rank, because these numbers are negative, so you actually have to like invert this relationship in your head. Else, if the parent of U is greater than the parent of V, oh wait, that's the same. If the parent of U is less than, then U has higher rank. Else, else down here, they have the same rank. So if they have the same rank, either of them can become the parent, and we just increase the rank by 1. So parent sub U equals V, and minus parent sub V, right? So we update it so U points to V. So V becomes the representative. V becomes the representative, and then increase its rank by 1. Increase V's rank by 1. That's what we would do there. Now, if U has smaller rank, then we want to attach it to V. So parent of U equals V, I think. If U has higher rank, then parent of V equals U. Is that right? And I don't have to do anything to the rank, because the rank stays the same in this case. Is that right? Oh, I'm coding without having the screen up again. At some point I'll stop doing that. Okay. So in this case, V becomes the representative, and it has the higher rank, so we don't change anything. Okay, this is right. I think this is right. So this right here is your basic. This actually isn't basic. So this is your. I hesitate to say fully optimized, but this is your union find algorithm that uses union by rank and path compression together. The path compression is down here in find representative, specifically where we update all of the, as we're trying to find a representative of like a path of nodes in a tree. As we're going through, we also update the representatives of all of them to be the root of that tree. And then in union, we get the representatives of both. If they're the same, we don't have to union, so we just return false. Otherwise, if U has smaller rank, V becomes the representative. If U has higher rank, then U becomes the representative. Is that right? Hold on a sec. If U has higher rank, yeah, it's right. It's right. Okay, so now that that's built, I can tell you right now, I'm gonna have to come back and make some changes to this for this problem. I already know what they are. Specifically, right now there's no way to, we're not keeping track of the sizes of the sets, and I'm gonna come back and add that. All we're doing right now is we're making it possible to create the sets, but after we create the sets by traversing through the input, you know, the island grid, after we create the sets of islands, then there isn't really a quick way to find the sizes of them without like traversing through all of the trees again. So instead of doing that, what we can actually do is we can come back to this union find code, specifically the union code, and we can add a little bit more logic to it so that when we merge two trees together, we also keep track of the size of the tree. It's easy to do. I'll show you how to do it later. More importantly, let's start actually using it. Let's see. Do I want to just finish this problem before I take a short break? Well, not really, because it's just going to be a short break. I'm just going to go fill my water and use the bathroom. Link the problem real quick. Yeah, for sure. That's actually, I should be doing that all the time. Also, Adnan445, welcome to the chat, and thank you for the follow. Yeah, so I'm solving this one. Also, you're my first follow since I added the daily follower goal, which was today. This is my first day using the daily follower goal. So it is good to see that it increased from 0 out of 5 to 1 out of 5. Yeah, let's go. Yeah, it's using stream elements. So I'm gonna take a quick break real quick, but since you just hopped in, I can just review for you what I did real quick. So I'm solving the max area of island, and there's multiple different ways to solve it. So I decided, just as an exercise for myself and maybe to make it more interesting for the stream, I would solve it in all three of the ways that I know how to. So I started off by solving it using a BFS with a Q. If I go to submissions, that was my first submission, which was accepted. I then added a DFS function, and I solved the problem again using DFS, and that was accepted. And so now, kind of as like the, yeah, exactly, DFS, BFS, union find, yeah. So these commented out lines of code down here are where I was producing the answer using BFS and DFS. And so now, just as an exercise for myself, because it's been a while since I implemented union find, I'm going to solve the problem a third time using the union find code that I just wrote. Yeah, I thought it was good practice. I think that assuming that this is right, and I don't have to debug it, which is that might not be an accurate assumption, but let's hope it is. I should be able to come back after the break and finish this pretty quick. Do you CP or just LeetCode? I CP a little bit. So if we go to my LeetCode profile, my contest rating is 1799. But if you look at the timeline, it's been a while. So I kind of I was CPing for a while right here. And then I stopped. But I'm getting back into it though. So I signed up for both of the contests that are on Saturday, and I'm planning to live stream those. Although if you're competing, I highly doubt you'd be there for the live stream. But I am planning on doing the contests on Saturday as well. So I want to get back more into the CP stuff. But yeah, I hope you stick around for like 2 or 3 minutes. I'm gonna be right back. I just need to use the restroom and grab some water. So I'll be right back. Okay. Adnan, do you CP? What, are you like pretty experienced? So when I'm when I'm doing this stream, I'm kind of gearing it to be a little bit more beginner friendly. So often I'll take some time to explain. Oh, code forces. Okay. Yeah. So I already spent quite some time like trying to explain path compression and union by rank and stuff like that. So uh, since you're experienced, that part of the stream probably might be a little boring or just review. But yeah, just wanted to let you know about that. Okay, so just to finish this off, uh, now that I have the union algorithm done. Oh, and code forces. That's like, I feel like that's like the next level stuff, right? Oh, I appreciate that. I appreciate that. That's definitely a compliment. Uh, yeah, like I as I said, I took a long break from this. Let's see, what was my peak? I guess I was like 1840 right here. Um, but as I get into it, maybe that'll continue to climb. We'll see. Okay, so Code Forces is like the really hard. Oh, Olympiad in September. Yeah, I always get pretty intimidated when I look at some of the Code Forces problems. I'd like to continue to get better so that I can hold my own in contests like that. The LeetCode is like the right level for me. I feel like they intentionally gear it to be beginner friendly. They'll have like one or two that most people should get within the time constraint, and then like more experienced people might be able to get question three, And then question 4 is basically just to add add a spread between the extremely advanced programmers. Yeah, yeah. And then even question 4, like I've noticed recently, question 4 in the LeetCode contests, the top coders are solving like the entire contest in like 8 minutes. So apparently their hard question is even pretty easy for like really advanced CPers. Oh, it's the same. Okay, gosh, I might have to check it out. I don't know quite how many contests I want to start signing up for, but we'll see. I might start signing up for some more. Okay, so the next part is pretty easy, assuming my union function and my find function are right. I just go through these cells one at a time in row major order, and I merge with the cell to the right, and I merge with the cell below. Yeah, exactly. I am preparing for interviews right now, so that's one of the main reasons I'm trying to review all of this stuff. So okay, here we go. So if the cell at ij is 1, then if I is less than n minus 1, and grid of I plus 1 j is also a 1, then we want to merge those. So union sets, and we pass in our parent array, and then I wrote this little util function here to get the node index from the coordinates. It's kind of a long name though, so let me just call it get index instead. Still got a few years. A few years till what? Till you are like doing technical interviews for like the job market? Oh, gotcha. Yeah, man, take advantage of the years. Take advantage of the years. I don't think that if I had the choice, I would go back and do all that again. But as prepared as you can get now, that's just gonna help you out. You know, if you can like get this stuff down packed and land an interview with Amazon or Google, and like you can do these questions without having to think about them, you're just gonna get the job. You know, I, J, N. And then get index. I mean, there's also the behavioral part of the job interview, but you can also prepare for that too. Like you can just study and prep for these interviews, and if you put in the time and you grind it out, you'll be fine. For sure, yeah, with time. Okay, so if I is if the next cell is in the bounds and it's also 1, then we union those. Is that right? And then the same thing for merging with the cell below. If j is less than m minus 1 and grid I of j plus 1 is a 1, then we merge these. Is it hard to get to 1500 rating on LeetCode? Honestly, I don't know. Can I zoom out on my rating timeline? It looks like in 2017 I was 1470. So honestly, what I would recommend is just sign up for a few contests and see how your performance impacts your rating, and then you can see if it's like trending upwards or trending downwards. But at the same time, don't like stress out about your rating, man. Just enjoy the process, learn how to do the problems, and eventually your rating will go up just naturally. Unions, okay. So that's gonna union the sets. Now, this is the part that I mentioned before. I also want to keep track of the size of these sets. So in order to do that, I'm going to create I'm going to create a parallel vector for parent, and this vector is going to keep track of the sizes of all of the sets. So all of the sets start off disjoint, and they all start off having size 1. And so what I'm going to do is every time I union, I'll pass in my size array, and I'll keep it up to date as I'm unioning the sets together. So I'll go up here to my union sets function, vector of int reference size. Okay, so if the sets are already merged, we don't have to do anything. Otherwise, we merge the sets, and so I need to update the size here. So size of u plus equals the size of v. Is this? I think this is right. No. This is backwards, because I'm making v the parent. Since I'm making v the parent, I have to update the size of v by the size of u. Similarly, when I make u the parent, I update the size by whatever the size of v is. So the idea with the size array is for any nodes that are representatives of their set, the size at that index should be kept up to date. It should be right. And then this is the last case, which is size of v plus equals size of u. And then I think now what I can do is I can actually update my answer here. Answer is the max of the current answer, and the size of the set at ij. I think that will work. Size of, and I need to get the index again using my util function. Yeah, let me add more comments here, because I'll have like a BFS approach. BFS approach, and then last but not least, union find approach. Okay, run the code. Let's see here. Line 9. Oh, is that just because this needs to be defined first? Oh, okay, and const is not a C++ concept, so we'll fix that. And okay, so we just have a couple of little bugs to fix before we get to actually run the code. Okay, there we go. Use the example test cases along with this one and this one. Let's just see what we get. It looks like it's working. Okay, it looks like it's working. I got the expected output for both of the examples, and I added 2 little test cases just to check. So let's submit, and let's see if we get our third accepted for the third approach. And we don't. Okay, so they have a test case here that it's failing for. So let's take a closer look at that one. Notepad. I'm just gonna save all my test cases in a notepad file. Yeah, F, right? F's in the chat. I'm probably messing something up with the sizes array. So I'm saying 4, but the answer should be 3. Let's have a look at this grid here. So it's, I just want to look at it in 2 dimensions. Let's see what we're doing wrong for this one. Okay, yeah. So the correct answer is definitely 3. There's 2 islands of size 3 in the input. So what's wrong? Something about the way I'm doing the sizes, maybe? Is this going to... No, because if we get to this line, we already know that the 2 sets are disjoint. So they both each have their own size. I should play around with LeetCode's debugger at some point. I haven't tried it before. Oh, wait. I think I know what it is. I think I know what it is. Because these 2 if statements right here are looking to the right and looking down. Right? So let's say that we're looking at this very first island in the input. We're looking to the right and we're looking down. Or is it... Oh no, it's this island. It's this island in the bottom right. So we're looking down, right? But then once we get to this node right here, I don't know if you can see really where my mouse is. We look to the right and we count it. We count it again. Is that it? Are we like counting it again? Either way, it might make sense to zero out the nodes in the grid that we look at, just to make sure we don't double count stuff. Maybe I should print out the contents of the sizes array as we go through. When am I going to apply for jobs? I've already been applying for jobs. I have a phone screen on Monday, which I'm a little nervous about. If I pass the phone screen, then I'll move forward to a full set of interviews. And it's going to be at Amazon, so I have my fingers crossed for that. If I don't pass the phone screen, then I look for other things, other companies to apply to. Okay, let's see. Thanks, man. I appreciate that. Like I'm because of these streams, and I still have several of them left, and the contests, you know, before the phone screen. I feel pretty good about the technical aspect, but I need to study Amazon's leadership principles, because I've been told that they take them very seriously, and there's quite a few. So I need to like review all of this stuff here: customer obsession, ownership, invent and simplify, blah 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 blah. I got to review all that and make sure that I'm prepared to answer behavioral questions that, you know, exemplify these qualities. Okay. Yeah, exactly. I've been more focused on the technical preparation than the behavioral preparation, but like you said, I got time. I got like 3 or 4 days left, so I will be spending some time. Like, there's just no point doing that on stream, you know, because I literally need to sit here and be like, when was there a time that I fell out with a coworker and how did we resolve the situation? And then I have to look at the principles and all that stuff. All right, I'm kind of bummed that that didn't pass first try. What's wrong with this? Because I know it's really close to being right. How are we getting 4? So more importantly, let's figure out which set is saying that it's size 4, and then see if we can figure out why we're counting 4 ones for that set. So let's just console log the sizes after every loop. Yeah, let's just console log the sizes here. For you know what? I'm gonna stop being lazy. Let's try out LeetCode's debugger for this. That seems like it's probably the right thing to do. So let's set a breakpoint. Where's the best place for a breakpoint? I'll just set a breakpoint here, and let's run the debugger. So union twice. So the approach that I'm taking is, because I'm iterating through the cells in row major order, so I'm going through all the rows one row at a time. If I encounter 2 1s next to each other, I want to merge them together. But also, if I encounter 2 1s above each other, I want to merge them together. So these are the 2 different cases for that. And that should handle all of the adjacent ones in the whole grid. Okay, so after the first iteration of the loop, what does size look like? Okay, that makes sense. That makes sense. So because we're in the top right of, we're in the top left of this grid, we already have a set that has size 3 because we were at this node and we looked to the right and we looked down. So let's keep going. Let's just keep going. Oh, okay. So that's helpful. So for some reason, size of this just went to 4, and we're only on. Hold on. Let's start again and see exactly when it goes from 3 to 4. So I can see the local variables here, which is nice. So at I0 J0, we've got a set of size 3 in the top right, which is correct. Then when we go to I0 J1, we still have a set of size 3. And then when we go to I0 J3, wait, why did it skip I0 J2? Oh, it skipped I0 J2 because I'm skipping tiles that are zeros. Okay, so this is interesting. So we get to this node in the graph, which should be an island by itself of size 2, but it's increasing the size of my other one by 1. It's joining it up with this island over here. Why is it doing that? Something's wrong. Well, we already knew something was wrong, but let's try to figure out what it is. So why when I is 0 and j is 3, is it trying to merge with the wrong set? So grid of I plus 1 j is 1. Union sets parent size, and when we get the index for I, j, and n, and we get the index for I plus 1, j, and n. You know what might be better? To see when these union calls are happening. Let me start debugging again, but I'm gonna break whenever a union happens. So let me stop debugging, start again. Okay, so we have this. So we have the first union happening. If I step over this, we'll see one element of the size array go to 2. So the fifth element of the size array goes to 2. So we continue, we'll get here. Now we'll see that exact same element of the size array go to 3. And it does. So that's the first 2 unions, which represents that top island in the top left. So now let's continue. And now we're at that other one. So we're at j equals 3, I equals 0. So we're looking at this element right here. And for some reason, this call to union sets increases the size of the wrong one. Why would it be doing that? Hold on, let me just review this size code again real quick. I hate debugging, but it's such an important skill, so I just got to figure this out. Size of u plus equals size of v. Okay, let's try to, let's see, can I make this bigger? What can I do here? That works. That's perfect. Okay, so I can now see everything. So should I step into this? I guess that's what I should do. I should step into this. The index logic also does need to be right. Oh, it's wrong. I think it's wrong. I spent a little bit of okay, let's just try it. I think the index logic is wrong. I think this needs to be j times n plus I. Because j is the rows, and then if you're not in the first row, you want to add n to the answer, right? So if j is 0, because n is the length of the row, and j is which row you're in. So if j is 0, we just want to get I. If j is 1, we want to add the length of a full row, and then I. If j is 2, we want to add the length of 2 full rows. Okay, let's try this. Let's try this. Let's just run this on the test cases, see if we do any better. Hey, that's it. That's it. Stupid index logic. Okay, let's run the code again on all the test cases. Let me know if that made sense. I was not computing the index correctly from the I and j coordinates. Okay, so it does pass all those test cases, so let's submit. And we got a wrong answer again. What the hell? Okay, well, we did get past another test case, so that is progress, but it's still kind of frustrating. Okay, so let me just run this test case by itself. And let's take a look at the grid that this represents. So 1, 0, 0, 1, 1, 1. Okay, so the expected answer is obviously 4. But we're saying that it's 3. So what we would expect to happen is when we're at this top left corner, we should union these two ones, right? And then once we get to this one, we'll union these two ones, which will put all 3 of these in the same set. And then once we get to this one, we'll union these 2 ones, which will put all 4 of them in the same set. 3:20 a.m. for me. Oh, yeah, dude, I'll be around tomorrow. Either around the same time I started today or earlier. But yeah, I'll be very happy to have you back. So that'd be great. Have a good night though. Sleep well. Okay, what's my uptime? Let me just... Okay, so I've been live for 2 hours and 22 minutes, and my local time is 6:21 p.m. So here's the plan. I'm gonna finish this problem right now, and I had some other problems opened up that I wanted to look at, but instead I'm gonna jump right over to the dynamic programming practice for the day, because I do want to make progress on those before I end the stream, and I have a feeling those might take a bit, so let's just try to figure this out first though. So maybe I should change my daily follower goal to be like 1 or 2. Maybe 5 is too ambitious right now. Maybe when I go live tomorrow, I'll do a daily follower goal of 2. Okay, let's see. Let's see. Let's do the same thing. Let's debug and let's break at the calls to union. Let's see what's going on. Okay, so this is the first one. So we'll be looking at these 2 vertical ones here at the beginning. And then if I step over that call, the size of the set increases to 2, which is right. So let's continue. Now we're at j equals 0, wait, I1 J0. Oh yeah, that's here. That's okay, so now it's trying to union these 2 together, and so when we step over, we get 3. So far we're right. So far it's unioned these 2 ones, and it's unioned these 2 ones. So the question then becomes, why don't we union these 2 ones? Because we should be doing that next. Okay, so we got to I11. We got to I1J1, which is this coordinate. And it's trying to union with this. And when I step over, okay, that's weird. So when I stepped over, it did update the size to be 4. Wait, what? That's weird. Did you see that? So my size array has the right answer in it, but that's not what I'm returning. Huh? How did that happen? I'm producing the correct answer in my sizes array, but it's not being incorporated into the answer. So my answer starts at 0. Then every time after I union twice, I try to update the answer with the size, but oh, big brain. We don't need to, we need to get the size of the representative of the set, right? Because in the sizes array, the way that I have it implemented up here, the only sizes that are guaranteed to be correct are the sizes of indices that correspond to representatives of their own set, right? Like the root of the tree, as we talked about earlier. So this actually needs to be size of find representative of sizes of get index. So first I get the index of the node that we just unioned. Then I find the representative node for that set, and then I get the size of that, and that should work. So let's get all the test cases back, and let's run it again. No matching. Oh, no matching call, function call to find representative, because I also have to pass in the parents here. Run the code. Okay. All right. So we have the expected answers for all of the test cases that we have. Let's try again. Let's try to submit. There it is. We did it. We did it. Yeah, we did it. We're good. Okay. All right, that's cool. So you know what I'm gonna do is, here's what I'm gonna do. I'm gonna do one last thing just for fun. Notice how for my BFS approach and my DFS approach, my answer update line of code is just one line long. So just to make it a little prettier, I just want to have one line of code right here. I want to have like answer equals max of, and then I'm going to call a function. I'm going to call a function right there. So let's take all of these lines of code, copy them, and we're going to make a function. It's going to return an int. It's going to be called handle union find solution. But we'll just call it solve with, no, not solve. We'll just call it do unions. I don't know, that's probably not a really good function name, but I'm calling it do unions. And so all of that logic goes in here. And then what we return is just the size of the set. Yeah, so we return do unions. So down here, answer is the max of answer and do unions. And like now the only other thing, which is glaringly obvious, is that all the variables that we're using here, we do need to pass in. So let's just go ahead and do that. Let's start with parent and size. So I can just copy the parameter like definition from up here, because those are vectors event references. So I'll pass in the parent and the size. And then what else do we need? We need I, we need J, we need N. Is that all of the stuff we need? Oh, we need the grid. We need to pass in the grid as well. So I'll copy my grid parameter from right here. I'll make that the first parameter. Let's just make this a little easier to read, so we can put all of our parameters on separate lines. Okay, so we've got our int do unions, takes the grid parent, size, I, J, N, takes all the stuff. We check our bounds. Then we union. We check our bounds, we check to make sure it's a 1. We union. And then we return the size of the representative node of that. And then the get index function will be in scope because it's right there. And let's see if that still works. That should be fine. Oh, okay. We do need to pass in n and m. So int n and int m. And oh, also very importantly, I need to actually pass those in right here. So grid. What were the? grid parent size I, J, N, M, semicolon. Okay, cool. So I like that a lot because it just makes it so it makes it so that I can, like, you know, I can just comment in the solution that I want to use really easily. So we'll leave it on union find as because that's the last one we did. I'll delete these lines of code, run it again, submit it again. Okay. So the union find approach does run slower than BFS and DFS by about 10 milliseconds. And that's because there is a lot more overhead to doing union find in this problem. And if you were doing this problem, like, you know, in a contest, it would make sense to just implement it the fastest way that you can, like the fastest way to code. And it wouldn't be union find. If I saw something like this in a contest, I would just jump straight to BFS or DFS and write it that way and try to get it accepted. Because I'm practicing, I wanted to review the union find approach. But then it's also important to note that union find is not necessary for this problem. It does work, but it's not necessary. Whereas there are other types of problems where the solution requires you to use a union find. So it's still a good technique to know, because even though you don't need it per se for this problem, there are problems that you do absolutely need it for. And I think, so I'm done coding for this problem. The last thing that I'll do is just take a look at the solution. Union find, very intimidating. Yeah, it is. Surdy's a lot 7. Hey, what's up? Thanks for hopping into the stream. I'm doing some LeetCode today. I've solved a couple of problems so far. I just solved 695 max area of island. Not a very difficult problem, but there are several different techniques. So I went ahead just for practice and I solved it all 3 of the ways that I knew how. So I solved it with BFS, then DFS, and then the one that took me the longest, because I had to review some concepts, was the union find approach. So I just finished that, and I'm going to be moving on to another problem here in a minute. But not enough study streams. I agree. When I first was learning about union find, I thought it was intimidating too. And like, I know I was going through an explanation earlier, and it probably wasn't very good. So what I would recommend is watch some YouTube videos about union find where people show you like graphically what it's doing. Like they'll show you graphically in a more beautiful way than what I did here. So if you want to learn union find, which I would recommend, just go watch some YouTube videos, and then after you kind of grasp the concept, go find, you should be able to sort LeetCode problems by the union find category. Yeah, you can. Yeah, I'll take a look at it. I did want to jump to some dynamic programming, but if you have a problem, I can take a peek, and I'm not going to guarantee though that I'll solve it right now. Surdy's a lot 7. Yeah. I like to code on LeetCode and C++. I don't solve every problem in C++. I also whip out the JavaScript and Python for some problems. But I like C++ because of the standard library. It's the standard library that I'm most familiar with. So, like if I need to drop in a priority queue or something, I just know how to do it quickly in C++ as opposed to other languages. That's cool. C++ at work. What do you do for work specifically that requires you to code in C++? Okay, not enough study streams. Let me take a look at the link you just sent. Okay, you sent me an easy problem. What I say easy, like I'm referring to the tag that LeetCode gives it. I wasn't saying that in like a condescending way. Okay, let's take a look. Given a string array words, return an array of all the characters that show up in all the strings within the words, including duplicates. You may return the answer in any order. So Bella label roller gives you ELL. Oh, I see. So basically, this is kind of like mathematically, you could think about this as like an intersection problem. Like you're trying to get the set of all, so for each word, you can generate a set of the letters that are in the word. It would be a multi-set. And then you want to go through all the words and find the intersections of all of those sets. I developed test automation and object detection programs for an automotive company, as well as machine learning models. Oh, are you doing like self-driving stuff? Only ML guy there at the moment, so have to do requirements, dev, and validation myself. That's cool, man. That's cool. Test automation, object detection, and stuff like that. Yeah, like ML is one of those areas that I like dabbled with. Like there was a time where I opened up Python and I threw together a couple of TensorFlow models, like not really knowing what I was doing. And it was fun, but I can tell that if I wanted to get to any reasonable level of skill with it, it would take a lot more effort to learn. But that's really awesome. I've been using machine vision to automate hardware testing and improving their autonomous driving software. That's cool. So, out of curiosity, are you based in San Francisco? Just because I know that there's a lot of self-driving like companies and startups around here. If you don't mind me asking, who do you work for? Oh, okay, in Detroit. So, are the autonomous cars street legal there, like they are here? Okay. Bella label. So we develop autonomous software and general car parts for our customers. Awesome. You guys make 1 million cameras a day. It sounds like a big company. That's pretty cool. Do you have customers in the Bay Area? Because literally every time I walk outside, like 3 autonomous cars drive by. So I'm just making an assumption. Your location focuses on cameras, radar, and LiDAR. Got it. It is really funny seeing the autonomous cars driving around San Francisco, because they all kind of look like they all have a nice company logo on the side, like Cruise, Smooth, stuff like that. But then all of the like gear, all the cameras and stuff kind of look like they've just been strapped on. But that's how you start, they gotta start testing somehow. So I guess you just buy the gear and strap it on yourself. That's cool, Surdy. That's cool. All right, let me take a look at this for Not Enough Study streams. What language do I want to use for this? Given a language. Oh, okay. I think I know what we can do here. So basically, what you can do for this one, study, is you can create like a frequency table for all the letters of the first word. And then you can go, after you do, and when I say frequency table, for Bella, you'd have like B equals 1, E equals 1, L equals 2, A equals 1. So you're mapping from the letter to the number of occurrences of that letter. Python has a really easy way to do that using a counter. Once you have that for the first word, you can just go through the rest of the words and decrease, basically decrease it, the numbers of the letters. And you're allowed to return the answer in any order. What types of jobs are you aiming for? Mostly like front end, like web development. That's what I've been doing for a while now, and I've been unemployed for a couple of months because I quit my job because I wanted to be unemployed for a bit. But now, for financial reasons and other, it's time to get back into working. Hopefully, on something that I'm excited about. So, yeah, I'm aiming for like front end or full stack jobs mostly. Yeah, yeah, it definitely was a luxury. So I was working for Google for a year and a half, and while I was working there, they gave me a bunch of stock that I didn't do anything with, and I looked at it and I was like, oh, you know what? I could quit and sell this, and like, I could just live off that for a little while. So that's what I've been doing. But I do need to get a job again before I become homeless. So that's why I'm back into the interview prep grind. You're technically intern and trainee. Got it. So, not enough study streams. I'm just gonna call you study streams. So study streams, you can, from collections, import counter. Do you want me to solve this in a specific language? Yeah, I quit. I didn't like it, man. I mean, I think that at that company, the level of enjoyment and motivation and passion you have for the job is really dependent on the product area and the team. A lot of people really love working there. I enjoyed it for a while, but I was working on some stuff that just wasn't feeling. And so yeah, Serti, you just pointed out one of the things that I was missing at my last job. I did not have the full creative freedom that I wish I could have had. Counter of words 1. So here, check this out, study streams. If I print this, so basically what I just told you about the frequency table, it's already done that for me. So it says that there's 2 L's, there's 1 B, there's 1 E, and there's 1 A. And so now we can use that as we look at the rest of the words to figure out where the intersections are. So for W, for word in words 1:. So basically just for the rest of them other than the first one. My boss just says, give me a model that does X and leaves me to it. Nice. And I'm also the only guy who can maintain the internal ML apps. Yeah. That's great. Like you said, job security, man. If you're at a company and a role that would have a hard time replacing what you do, it definitely gives you a lot more freedom and less stress. And if something takes a little longer than they would like, what are they gonna do? They can't replace you. So that's great. Okay, so I think what I'll do is here. So this counter will actually be a representation of the answer, and then we'll create another counter for every other word. So we have our answer. And the thing to keep in mind about the answer is that before we return it, we do need to process it back into a list. So we'll have our actual answer, which will be a list, and then we'll return that down here. Once I graduate, they want me to be the feature owner for ML. That's sick, man. Yeah, it sounds like even pre-graduation, you're a pretty valuable hire for them. And it's great that you already have like work lined up for after you're done graduating. A lot of people don't have that. So we're gonna make our actual answer. So for letter in answer. Okay, these variables are not named well. We'll call this the answer counter because it is still technically a counter. And then we'll call this the answer. So the answer is just the list of letters, like that. So for the letter in the answer counter, we want to append to the answer that letter. Can we do, wait, is this the thing? Letter times answer counter letter. So we basically want to take the number of that letter from the answer counter and put that in the list. I don't remember if I can do this in Python. Oh, it created a string. Let's see. There's probably a nice little nifty Python way to do this. Python create array of n identical elements. This is it. This is it. You can. So what I was doing was I was multiplying a string, which just creates another string with a certain number of instances. What you actually want to do is multiply a list. And then you want to concatenate all these. Is there a Python list concat? Python list concat. Oh, you can use the plus operator to concat. So we can actually do this. Answer plus equals that. So now this is what we want right here. So we haven't actually finished the problem yet. We still have to implement some code up here to take letters out of the answer counter. But once we finish that code, this right here will produce the answer. And right now, because we've only looked at the first word, we have our answer as B-E-L-L-A. And then the goal will be to look at these other two words, and ultimately we will remove the B and the E from the answer counter, and it'll just be left with L-L-A. Or sorry, we will remove the B and the A, and it will be left with E-L-L. And that will pass the first test case, and then we hopefully will pass the second one as well. Once I graduate, they want me to be the feature owner from Alia. It does feel kind of weird since I'm surrounded by people with PhDs. Yeah, that can be intimidating. Hopefully that's also a good learning opportunity. What do they have PhDs in? Like, is there like opportunity for you to learn from them, or is what they do completely different from what you do? Okay. So back to this. Physics or electrical engineering. I gotcha. Man, you got physics PhDs where you work. That's intense. Like, yeah, that's even more intense than. I don't want to shit on any like areas of study, but I was gonna say being surrounded by physics PhDs is more intense than being surrounded by like history PhDs. The physics PhDs work on image quality. Got it. Okay, I'm really close to having this, so let me just try to knock this out real quick. So we get to label, right? We get to label and we create a counter for it. So we'll have it will contain two L's, one E, it'll contain an A and a B. And the goal will be to recognize that the B and the A need to be removed. Well, but they actually don't need to be removed because label and Bella have the same letters. So once we get to roller will be when we expect the B and the A to be removed. So I think what we can do is iterate through the elements of the counter. And then oh, no, we need to Yeah. So so that was right, except what we can do here is we can iterate through the letters of the answer counter. So basically, like, let's assume that we're at roller, right? But we've already processed Bella and label. We're gonna iterate through the BELLA. But for each letter in the answer counter, if we have less than that same number of letters in the current counter, then we need to remove it from the, we need to decrease what's in the answer counter. So what we can do is if the letter is also in the counter for the word, hold on a sec. So we're iterating through the answer counter. So let's say that we look at B. We would see that B is not in the word counter. So if it is in the word counter, it needs to be the same number or more, right? It needs to be the same number or more. So if letter is in counter, it's hard to find optics researchers and engineers. Gotcha. Yeah, that sounds like it's probably a niche, like a niche area of expertise. Hold on, how do I write this as simply as possible? So I'm just trying to think about it in terms of Bella. So I'm looking at Bella and I'm looking at roller, and I see that like the B is not in roller, so I remove it, right? That's kind of what I'm supposed to be doing. If I'm looking at Bella and I'm looking at roller, if I see that the B is not in roller, I remove it from the answer counter. So if not letter in counter, let's call this the word counter to distinguish it a little bit better from the answer counter. Then how do I delete from a counter? Can I just do this? Delete answer counter letter? Is that legit right there? It doesn't want me to delete from the answer counter while I'm iterating. Oh, okay, I can't delete from it, but I can just subtract, right? I would be able to do answer counter. I could do this. I could do answer counter letter equals 0. Else if, okay, and then this is the other part. If the number of instances of that letter in the current word is less than what we have in the answer counter, then we just need to set what's in the answer counter to the minimum. I don't need to have a special case for that. So here's what you can do here. You can do else answer counter letter. You can do answer counter letter equals the min of the answer counter letter and word counter letter. Okay, so that works. That's how you would solve that. Well, I don't want to start saying that's how you would solve that problem without submitting it. But there was something else I wanted to try. So let's submit. Okay. So study streams, that's how you would do that one. Let me know if that makes sense. I can like dive into it a little bit more. So what I wanted to try though, because I might be able to delete a couple more lines of code here. Specifically, since I'm doing this right here, I'm setting the answer counter for a specific letter to the minimum of what we already have for that letter and what's in the word. But word counter sub letter might return 0. I think counter is probably smart enough to have like these lookups return 0 if it's not in there. And if that's the case, we're about to find out. I could probably just do this. I could probably just do the min right here. Yeah. So that works. Let's get a couple of runtimes. It's good enough. Like it's not running significantly slower than other Python submissions. So from the high level, basically what you're doing is you're starting off and you're taking the first word, which is Bella, and you're just saying like, okay, Bella is the answer. Bella is all of the characters that show up in all the strings, right? You just make that assumption. That's what I'm doing here by turning Bella into the answer counter. And then you look at every other word after the first word, and then you update your answer counter whenever you can't find repeating letters. So thanks for throwing me that one. That was honestly kind of a nice little break from what I was doing. Okay, so max area of island we also finished. The only other thing I was going to do real quick, I was just going to look at the solution page, because I think what I'm expecting to see here is the same 3 things we did, which is the BFS, the DFS, and the union find. By the way, I will just say thanks for hanging out in the stream. It definitely makes it more interesting when people are talking in the chat. And I'm happy to hear about like you guys' lives and you know, your software journey, your programming journey. Okay, so approach 1 is the DFS, which we did. Approach 2 is the DFS, which we did. Oh, they do an iterative DFS. That's actually something I don't think I've ever written a single time. Usually when I do DFS, it ends up being a recursive function call, which is what I have here. But there are ways you can do an iterative DFS without recursion, and that's how they decided to implement it here for the sample solution. And okay, so they don't even mention union find as an approach in the solution, but it obviously is an approach because we solved the problem that way. Yeah, no need to look at any of that. You also know that it's union find because they list union find under the related topics as well. Okay, so I had a couple more problems here that I wanted to look at, but I think I'm gonna put these aside for now and at least take a look at the DP programs that I wanted to solve for today. So I'm just adding these other problems that I thought looked interesting to my my bookmarks, because I might come back and have a peek at those, or I might not. They might just go and live long, boring lives, lonely and isolated in my bookmarks folder, because I might never go back and look there. I never run out of like interesting problems to solve on LeetCode. Okay, so the plan for the stream had been to do some like warm-up problems, which are all the problems that we've done so far, and then look at these 3. But it is also, I've also been live for a while now. I don't know if I'm going to be able to do all of these 3. Hold on, let me just send a quick text. Hold. Just make sure that none of these DMs or text messages are important, and it looks like we're good. Okay, so are linked list questions common in interviews? I've never had one, but supposedly every once in a while companies like to ask you stuff like reversing a linked list. Like the concept of a linked list is important. So I would say you should, if you're prepping for interviews, you should at least put that on your list of things to learn. You know, like make yourself a list of topics to study, and put linked lists on there for sure. Like you probably don't need to be a linked list expert. You probably don't need to build a linked list class from scratch, but I wouldn't go in there expecting with 100% certainty that they won't ask you anything about a linked list, because they might. Interesting linked list problem is the finding a cycle in a linked list. Look that one up, because the solution to it is actually it's pretty cool the way that they solve that problem. So like you're given the first node of a linked list as input, and they just say you just have to return like Boolean, true or false, whether or not the linked list contains a cycle. In other words, like, you know, you're going through the nodes of the linked list, blah, 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 and then like out of nowhere, one of them just like loops back to halfway through the linked list where you already were earlier. You should probably take a look at how to write the code to detect that. It's not intuitive. You probably end up looking up the solution. That's what I did. But once you like read what the solution is, you're kind of like, oh, duh. So, house robber. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Interesting. So basically, there has to be at least one space between the houses you rob. There has to be like at least one house in between. And the right. Okay, so this is just the amount of money in each house. So I think so. We have to model this problem as a DP problem. So we're gonna have DP of I, and we just want to define what DP of I means. And I think DP of I is the amount, the max amount of money if from robbing all of the houses, from robbing as many houses as possible, just from robbing houses, right? DP of I is the max amount of money from robbing houses, 0 through I. Right, not all of the houses, because you have to skip houses. Mega team's coming in. What is mega team? I'm a new. Sorry, I'm a noob. Is that a raid? I didn't see a raid come through the activity feed. Well, what's up, mega team? Hope you guys are doing well. Where are you guys coming in from? Should I Google what mega team is? Okay, I don't think Google is going to provide any useful insight on what mega team is. Okay, so, well, for any first-time viewers, I'm solving LeetCode problems live right now in preparation for technical interviews. And I think probably, just based on how long I've been live and how late it is, this is probably going to be the last problem I attempt. Although I had hoped to do all three of these DP problems. My brain is already starting to fizzle out, unfortunately. So I'm trying to solve LeetCode number 198, house robber. And so I'm structuring my solution as a DP. And we're trying to figure out what's the max amount of money we can rob without alerting the police. And in order to not alert the police, we cannot rob two adjacent houses. And so structuring my solution as a DP, the way that I like to think about it is I have a DP array, right? It's just going to be an array of probably the same length as nums. And so DP sub I is going to represent the maximum amount of money from robbing all the houses from the beginning of the street through I. And when you think about it that way, what you can do is, so since it's the max amount of money you can earn from robbing houses, so it would be, so let me rewrite this a little bit. You're gonna rob some houses 0 to I. You're gonna rob some houses 0 to I minus 1, and you will rob house I. So that's the way you want to think about it. So DP of I is the max amount of money from robbing some houses 0 to I minus 1, and you will rob house I. So because of that, we already know that DP of I includes nums of I, right? Nums is the amount of money in each house. So since we've defined our DP such that we will rob house I, we know that DP of I is going to contain nums of I. But then what else does it contain? So it cannot contain house I minus 1. So we could put I minus 2 here because we cannot rob house I minus 1. If we rob house I minus 1, we've violated the requirements and the police will be alerted. Where am I from? I live in San Francisco, California. I've only been here for about 7 or 8 months, but that's where I reside right now. Previously, I lived in Colorado Springs, Denver, and New York City. How about you, Casper141? Oh, also, thank you for the follows. Thank you for the follows, Casper141. Why are my alert sounds not playing? I'm supposed to be getting alerts on screen and a little ding every time I get a follow. I'll have to look into that later. My apologies for that, because anytime a follow comes in, I do want you guys to be recognized on screen for that. Oh, my latest follower is also not working. All right, so I'm having some issues with the overlays. I apologize. I'm a new streamer, so I'm not entirely sure why those aren't working. But again, thank you, Casper, Isn't It Eric, and Dr. Fin69 for coming into the stream and following. That puts my daily follower goal to 4 out of 5, which like 2 hours ago I thought was ambitious. And now you three came in and threw me a follow, which, yeah, thank you so much. I really appreciate it. Now I'm only 1 away from the follower goal, and honestly, if I don't hit it, if I just end up with 4 out of 5, I'll still be really satisfied. So yeah, that's where I'm from. What about you three? You guys all came in together, right? Yeah. So did you guys just come from another stream? If so, what were you up to? I'm assuming it was probably something software development related. And hope you guys are having a good day. Feel free to participate and to be active in the chat or just watch. I'm just happy to have you guys here. All right, so DP of I will contain nums of I. It cannot contain nums of I minus 1. So, but then it can contain nums of I minus 2 or nums of I minus 3. So it's actually going to contain the max of those. Oh, wait, there might be a better way to structure this. Because we can either rob the current house or we don't. Oh, nice. That's cool. Cool. Well, thanks for bringing your friend group in here, Eric. I'm structuring this wrong. Here, let me restructure this. So DP of I is actually the max amount of money from robbing houses 0 through I, from robbing some houses 0 through I. So I'm going to redefine my DP to be structured that way. They're all future developers, even though they don't like it. Love it. Yeah. Push them in the right direction. There's definitely a lot of great opportunities career-wise in the industry. You know, you know, you can make good money in the industry. You know, after you put in the time, get some experience and stuff like that. So the job market's very competitive. So yeah, I agree. Eric's friends, Casper and Dr. Finn, you guys should be developers as well. Okay, so I'm restructuring the DP. So the max amount of money from robbing some houses 0 to I. That's the way I'm defining it. And so because I'm restructuring it that way, now DP of I may or may not include the money in house I, right? So it might include the money in house I, but only if we don't rob the previous house. So it's going to be nums of I. If we rob house nums of I, then we can't rob the previous house. So we would add to it DP of I minus 2, right? So this is basically saying we're robbing house I, which means we cannot rob house I minus 1. This one is going to be top down, I think. That's the way that I'm imagining it now. But hopefully I'll be able to explain it in a way that people will be able to follow along. And I'm also figuring it out as I talk too. So if we rob house I, then DP of I is nums of I plus DP of I minus 2, right? Because we cannot rob DP of I minus 1. Oh, wait. No. This is not going to work. This is not going to work. Because DP of I minus 1 doesn't guarantee that that house wasn't robbed. Okay. Let me go back to my previous definition. DP of I is the max amount of money from robbing some houses 0 to I minus 1, and you will rob house I. Okay, let me go back to thinking about it this way. So in that case, DP of I will be nums of I, and it'll be plus the max of DP of I minus 2, because since we're robbing house I, right? That's what this means. We're robbing house I. That means that we can't rob house I minus 1. So we have to go to either I minus 2 or I minus 3. Is that right? Maybe there's a better way to structure this. It's just to like structure the DP. Okay, so if I were to do it this way, this actually already is looking weird. Like having to look back that many elements in the DP array for a problem like this doesn't seem right. If I were to structure it this way, then the answer would be DP of n minus 1, or it would be the max of DP n minus 1, or yeah, it would be the max of DP n minus 1 n minus 2. It'd be, yeah, okay, so it would be that. So here's an interesting way to think about it. I think you're guaranteed to rob a house. So let's say that you have some houses, right? We have some houses right here. Let's just use these houses. So you got these houses. Let's say that you decide to rob this house. I'm using 1 for rob. I'm using 0 for not rob. And then let's say you decide to rob this house. because of this, you're guaranteed to rob this house, right? There's no houses with negative amounts of money. So that means that there's always going to be a maximum of 2 houses next to each other that you don't rob. Because if there's 3 houses next to each other, you just automatically rob the one in the middle. I think this is gonna work. I just don't think it's the prettiest, most intuitive solution. Let's see here. No, I mean, there's gotta be a better way to do this. I'm just not, see, the problem is I'm not structuring the DP in the most straightforward way. So let me just think about this for a second longer here, and I'll try to get to the point where I'm ready to start writing some code. You're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint is that you can't rob adjacent houses. What are some of the other ways that we could do DP of I? Anyone got any ideas? Chat is free to participate in brainstorming, especially problems like this where I'm not even 100% sure yet how to do it. So there's got to be like a nice way to do this. So DP of I is, let's just think about it this way again. It's going to be the max of what if it's like the max of DP of I minus 1? This is I think I had this written out before, but then I discarded it. Keep another state variable to keep track of whether or not the previous house was taken. Is it brute force? We might end up needing to do something like keeping track of. Honestly, like my brain is kind of saying maybe we need like 2 arrays. But I don't think it's necessary. I think there's a way to solve it without having to do that. Plus nums of I. So if I were to do it this way, that means that DP of I rob the house. Yeah. Okay. So what you said, I think is really similar to what I think I might have to do. So we could have like DP of I is the max amount if...
Sorry, you can't send announcements from this device yet.
Well, that's good to know. It's the max amount if like we have like a DP1 is the max amount if robbing house I, and then like DP2 is max amount if not robbing house I. And when I say max amount, I mean like the max amount of money you get after going from 0 to I minus 1. And then the reason I think 2 DP arrays like this would be useful is because as I think they need to reference each other in the loop. So okay, so I think that might be right. So let me actually start to write some code here. So And then this is pretty similar to kind of maintaining a state as to whether or not you're like definitely robbing a house. But instead of having like a bool, I just have like one of the DP arrays represents that I rob a house, and the other DP array represents that I don't rob that house. So n equals nums dot size and for I is 0, I is less than n plus I, and then we need our arrays. We need two DP arrays, so we have vector of int dp1 of size n, and so because this is a maximization problem, I think we could just start all of these off at -1. There's no negative numbers, so we don't have to worry about that. And then DP of 2. And then let's think about a base case for a second. So DP1 of 0 means that the max amount of money if I rob house I. So if I rob house I, that's going to be nums 0, right? Then DP2 of 0 is the max amount if I don't rob house I. So since I'm not robbing house 0, it's 0. So then let's just try this. Let's start the loop off at 1, and then dp1 of I is going to be, I just have to make sure I don't get these two vectors confused in my mind. If I rob house I, then that okay, yeah, I think this is right. If I rob house I, then I didn't rob house I minus 1. That's the idea. So that means that dp1 of I is num sub I plus dp2 of I minus 1. That feels right. Right, so dp1 of I means I'm robbing house I, so I take the money that's in there, and then it's the max money, it's the max amount of money from the other array, which is where I did not rob house, the house. Okay, so then what is dp2 of I? So in that case, dp2 of I means I'm not robbing house I. So if I'm not robbing house I, what's the best that we can do? The best that we can do is we can rob house I minus 1, right? Which is that. Wait, where's my max call? I feel like this problem definitely needs a max call in it. So if I'm robbing house I, then okay, well let's just, you know what? Let me just run the code and see how far off we are, because I don't think this is right yet. The other important question is, how do we get the answer? So the answer is either going to be that we rob the last house or we don't rob the last house. So it's going to be the max of dp of n minus 1 and dp1 of n minus 1 and dp2 of n minus 1. What do we get if we run this code? Okay, so I don't want to get excited by that because this happens a lot, you know, you like run the first test case and you get a good answer and then you're like excited, and then you run the second test case and it's wrong. Okay, now maybe I'm getting a little excited now. So this code produced the correct answer for the two examples that they give. So let's cross my fingers here for a second and submit. Okay, it's not right. It's not right, but we're on the right track though, because it wasn't just out of nowhere that I solved the 2 sample test cases. So I did not pass this test case 2112. So let me paste all my test cases up here and just take a look at this test case by itself. And hopefully by looking at it, it will expose what's wrong with my program. Let me get rid of all that too. I'll just leave these 2 comments here. So for 2112, let's see. Let's just think about 2112 for a second. Those are the amounts of money in the house. So the expected answer is 4, which makes sense because just by looking at it, you can see that if you robbed the first house and the last house, you would get 4 money. But I'm saying 3. So what I'm gonna do here is I'm gonna log my DP arrays. So let's see out DP1. For int x of DP1, see out x followed by spaces, and then we have a new line at the end. We'll have 2 new lines at the end. And then we'll log DP2 as well. And let's just see what we get. Okay. All right, let's try to parse this here. Okay, so DP1, which means we rob house I. So 2, 1. Is that right? So if we rob the first house, we're at 2. If we rob the second house, we're at 1. Hold on, let's just focus on DP1 for a second. If we rob the third house, it's saying 3. Is that right? So if we rob the third, yeah, that's right. Because if we rob the third house, that means we robbed the first house and the third house. So that would have been 3. And then let's look at the last one here. I think, so I'm pretty sure I'm just missing some little thing here in these 2 lines of code. Like there's like a situation, there's a robbery situation that I'm not taking into account. Okay, so if I rob house I, then I take the money, and then I return the max for not robbing the previous house. And I don't have to do a max there because DP2 should already be the max for not robbing that house. Now, I'm probably missing something on line 16. If I don't rob house I, then it's the max for DP of I minus 1. Is it hold on, let's try something. It means I could rob one of the previous 2 houses. Wait, no. If I don't rob house I want to know what so DP of house I is the max so far for not robbing house I. Then it's just going to be. Oh wait. Is that right? This is definitely the last problem I'm doing for the stream. I'll do those other two dynamic programming problems tomorrow. I'm not going to give up on this just yet, though. Also, just for context, dynamic programming is one of the areas that I know I need practice and review. So, hence the struggle that I'm going through. So, if I don't rob house I, then the best that I can do is robbing the previous house. Is that right? That's what this is saying. This is saying that if I don't rob house I, the maximum money is that I rob the previous house. Is it? Oh, sometimes you skip 2 houses at a time. So is it the max of robbing the previous house and the one before that? Is it that? Because you can skip 2 houses. Is that what I'm missing? So basically what I'm trying to represent here in the code is that I don't rob house I, right? But that doesn't necessarily mean that I definitely rob house I minus 1. I might actually be skipping 2 houses, because that's what I was talking about earlier. So let's just say that let me just try to conceptualize this. Let's say that I had this many houses, right? Like this right here, where 1 means rob the house and 0 means don't rob the house. This would never happen. This would never happen, because if you have 3 non-robbed houses next to each other, it's always better to just rob the house in the middle. So this would never happen. But this right here, this would happen. Sometimes it's optimal to skip a house, to skip 2 houses. So maybe the problem is that for the case where I don't rob house I have to take into account that I might also not rob house I minus 1. So, oh, is it this? Is it this? Okay, so the max I can possibly rob if I don't rob house I is if I either I do rob house I minus 1, but I also might not rob house I minus 1. That's okay. Let's try that. That seems like it might work. That gets me the right answer for that test case. Let's get all the test cases back. Also, I just realized it might have taken me way too long to figure that out, because yeah, exactly. DP. Yeah, it's a struggle. I have if you want to see my favorite YouTube video on DP, I'm happy to send it to you. I'll just link it in the chat right now. There's this guy, it's like an MIT professor, and it's like just a free lecture that they posted from his course online, and he explains DP in a way that really helped me. I'm just gonna link it. So let me see, MIT dynamic programming. Let's see. Yeah. So there's actually several installments. So if you get all the way through the first video, which is 51 minutes long, and you still want to keep going and learn more about DP, he has okay, yeah, here we go. So this is lecture 19. Right here, the first recommended video is lecture 20. It's the one right after this one, which goes even more into detail about dynamic programming. But this guy's hilarious. I don't know if the audio for him is coming through, but he's a really fun teacher. He's got a cool personality, and he explains dynamic programming in a way that historically has really helped me. So I'll just link that here in case anyone wants to take a look. And okay, let me just get back to trying all of the test cases and see if I get this one accepted. Why is it taking so long to run? Okay. For a second I was like, how did I introduce a TLE here? How did I create an infinite loop? Okay. All right, so we solved that test case. We're still passing the previous two, so let's try to submit again. Pogs in the chat, if anyone feels so inclined. So that's the solution. That's the solution. The weird part of the solution was to recognize that if you're not robbing house I, that doesn't guarantee that you're robbing house I minus 1. So the DP for the DP2 sub I is actually the max of robbing the previous house or not robbing the previous house. So I don't. Let me add a comment here just to see if it helps a little bit with the understanding. So if rob house I, then don't rob house I minus 1. That's exactly what this line of code means. So DP of I means that we take the money that's in house I, we add it in, and then we also add in whatever the maximum number of money that we can get is for not robbing the previous house. On the other hand, if not rob house I, then either it's so weird to write, but it's either rob house I minus 1 or don't. That's kind of that's what this line of code means. So DP2 of I represents the max amount of money that you can make by getting to house I. You're walking up the street starting at the first house. You get to house I and you don't rob it. If you don't rob it, then the max amount of money you can possibly have so far is either that you robbed the previous house or you didn't. So it's DP1 of I minus 1 or DP2 of I minus 1. Then after you get all the way to the end, the answer to the problem is the maximum amount of money you can make either from robbing the last house or from not robbing it. And that automatically takes into account all the different possibilities. So that's at least that's how I coded it up. I'm going to leave those comments in there. The runtime is really quick. Like that definitely means that this is the solution they were looking for, at least complexity wise. Let's have a quick look at what they talk about in here. So this looks like it's going to be a nice graphical explanation of what we discovered while coding this up. So let's skip that. So as we know, you could also do recursion with memoization. So study streams, honestly, if I had more brain power left, I would rewrite this as recursion with memoization for you, but I think that's probably it for me for LeetCode for the day, unfortunately. And then approach 2, which they just call dynamic programming, is the iterative solution. Base case initialization. Okay, so there's a way that you can code it up, apparently, where you just need one array. Oh, weird. There's a way you can code it up where you need just one array, but the way that I was conceptualizing it in my mind, having 2 arrays is just what I came to, you know. I don't know what to say. That's what I came to, and it's accepted, so I'm happy with that. Let's see if we can figure out how it works with one array real quick. So they initialize it to the length plus 1. The base case, okay, so they're assigning two variables at the same time, which is usually something nice you can do in Python, but when I look at this line of code, I'm kind of confused about what it's doing at first. But they're saying that the max robbed amount for n is 0, and they're saying the max robbed amount for n minus 1 is nums of n minus 1. They're doing this backwards. Which is, you know, you can do it forwards, you can do it backwards, like literally whatever way makes sense to you. You can do it recursive with memoization. In this case, it made sense to me to implement it doing forwards. Most important thing is just being able to get to a solution, regardless of you know, the specific technique. So the max robbed amount I is the max of max robbed amount I plus 1 and the max robbed amount I plus 2 plus nums of I. So this is what I was actually trying to figure out in the beginning, and then I couldn't, and that's how I ended up with having two different DP tables. But they're basically saying that this is for not robbing the next house, and no. This means you robbed the next house. This means you didn't rob it, and you're robbing the current house. Also interesting to note about this is because of the way they structured the problem, they have to look 2 ahead, right? So max robbed amount sub I depends on max robbed amount sub I plus 1 and max robbed amount sub I plus 2. And because their DP depends on 2 away instead of just 1 away, that's why they have to initialize 2 values in the array. So I guess my solution gets around that by using the 2 different arrays the way that I did. And because I'm using 2 arrays, I only depend on 1 away. Like if you look at both of these cases for I, the farthest away that I have to look is I minus 1. So that's actually, I bet that's probably like a trade-off that you could prove. I think if you only want to look 1 away, you probably have to have 2 arrays, and if you want to look 2 away, then you can do it in just 1 array. That my intuition tells me that that's like something that you could probably prove if you wanted to. Space 3, optimized dynamic programming. Okay, so let's see what is optimized dynamic programming here. Oh, okay. So when they say optimized, they just mean optimizing the space. They basically just rewrote their previous solution such that they're actually just keeping track of the last 2 values. And all that does is it improves their space complexity to constant rather than it being linear. Whereas if you have an array, obviously that takes O of n space, and I have 2 arrays, which is O of 2 of n space, 2n, but that's just O of n, it's the same. Okay, alright, well, unfortunately, if my brain wasn't as frazzled, I would do more, but that's the last problem I'm solving today. Let's just go ahead and see how we did. Yeah, I only solved 4 problems today, but that's because I spent a while on the max area of island. No, 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 dude. I appreciate it though. Um, I spent a long time on this one. Like, I had this one accepted quite quickly with the BFS, but then I spent a long time building the union find solution as well. So I think that's hopefully that wasn't a waste of time for me or for anyone else. But it was good for me to review union find, so I'm kind of glad I did that. But yeah, so we had an easy problem. Then we had the BFS, DFS, and union find one. Then study streams. You threw me the find common characters problem, so thank you for suggesting a problem. Viewers are always welcome to do that. Not that I'm guaranteeing that I'll do every problem that appears in the chat, but if I look at it and it looks reasonable, or if it's relevant, to what we're doing, then for sure. And then last but not least, I did get the house robber. So tomorrow I'm gonna come back and I'm gonna make up for the two DP problems that I didn't do today. So I'll come back and I'll do house robber 2, and I'll come back and I'll do delete and earn. And yeah, that's basically it. So study streams, you've been here like the last 2 or 3 streams. So thank you for being so consistent and coming to hang out. I do appreciate it. Having people in the chat makes it much more interesting. And everyone else who came by and followed, thank you. Anyone else who's still here, thank you. I'll be live tomorrow again with more of the same, and we'll just see how it goes. Yeah, no, I appreciate it. I appreciate you coming back like so frequently. I don't have VIP badges because I'm not an affiliate. Hopefully at some point I'll be an affiliate. And when that happens, people who are here all the time hanging out, I'll probably just give you VIP. All right, well, thank you everyone for being here. I'm going to go and relax my brain for a while because it's kind of frazzled. And I'll see everyone tomorrow. I'm going to switch to the stream ending stream for a short period, and then the stream will be over. So, all right, peace. Thanks for coming.